Zeal Education Society, redefining excellence.
Good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. In today's video lecture, we are going to learn the speed control of three-phase induction motor by various methods. Now, the various number of methods are available to control the speed of the three-phase induction motor, that is on stator side as well on the rotor side. The stator side, the methods are by changing the supply voltage, then by changing the supply frequency, by changing the number of stator poles, and V by F control. Also on the rotor side, there are the rotor rheostat control, that is just like a rotor resistance starter used for the slip ring induction motor and cascade operations. Now see, the stator side, this can be used for the squirrel cage motor speed control, and the rotor side that is only used on the slip ring induction motors. Okay. Now let us see one by one by changing the supply frequency. Now by changing the supply voltage, practically the induction motor is created as a constant speed machine. Now the speed control affects the loss of efficiency and poor power factor. However, the torque of a three-phase induction motor is given by T equal to K phi SE2 R2 upon R2 square plus SX2 square, where here if R2 is constant and slip is very small, then the term SX2 bracket square becomes very less as compared to R2. And therefore, the torque is proportional to SE square, and as E is proportional to V, therefore the torque is proportional to SV square. And for a constant load torque, then torque equal to S1, say T1 proportional to S1 into V1 square, T2 proportional to S2 into V2 square. Therefore, for a constant load torque, in order to maintain the constant torque, S1 into V1 square equal to S2 into V2 square. If V2 is decreased, in order to maintain the constant torque, S2 has to increase. So S2 increases and therefore speed falls, because the slip equal to Ns minus N upon Ns. So as the speed decreases, slip increases, or as the slip increases, speed falls. Now the same thing has been written here. If the voltage decreases, the torque decreases, and therefore for the same load torque, slip increases with decrease in V, and therefore the speed decreases. Now this method is rarely used because the large change of supply voltage is required for small change in speed, and the large change in supply voltage affect the flux density and magnetic conditions of the air gap. Now the next method is by changing the supply frequency. We know that synchronous speed Ns equal to 120 F upon P, that the synchronous speed is directly proportional to supply frequency. However, what happens by using this method as the frequency decreases? The reactance X equal to 2 pi FL. As the frequency decreases, the reactance decreases, and as the reactance decreases, what happens? The motor current becomes too high. It becomes too difficult. And if the frequency increases beyond a certain limit or its range, the reactance increases, and therefore the torque decreases, because the maximum torque is inversely proportional to the reactance. As the reactance increases, the torque decreases, and as the torque decreases, speed increases. Now the next method is by changing the number of stator poles. Now this method can be adopted only for a squirrel cage motor or a motor employing the squirrel cage rotor, because the squirrel cage rotor can easily adopt itself any number of stator poles. And this can be generally used for the stator adopt 4-pole as well as 6-pole windings on the same stator slots, in the same stator slots. For the 4 poles, for a frequency of 50 Hz, the speed is 1500 rpm. Whereas for the 6 pole, the speed will be 1000 rpm. So the speed obtained by using this method is very large steps, 1000 to 1500, and therefore it is not preferred. Okay, the most popular method is phi by f control. Just now we have seen phi by f control, that is the most popular used method in the worldwide. The ratio of phi by f must be kept constant in order to maintain the constant air gap flux and thereby the constant torque. The reason is the torque is proportional to phi Ia, and the EMF induced in the induction motor is 4.44 kc kd phi f tph. Now here, for a certain particular machine, this 4.44 kc kd t number of turns are constants, and therefore, and this phi can be replaced by phi into a, and therefore B is equal to k E by f, and this can be written as B proportional to phi by f, and B is also proportional to the flux, or you can say flux density. So what is happening if the voltage is kept constant and only the, if voltage is kept constant and only the, just a minute, if voltage is kept constant and frequency is reduced, so the flux density will increase, that will get saturations. Or if the frequency is constant and voltage is reduced, flux density becomes too small. And in order to have a constant load torque, the flux, air gap flux should be maintained constant. And therefore, the phi by f ratio, that is variable voltage, variable frequency. If the frequency is varied, the voltage is also varied, so that the ratio V by F should be maintained constant. And this can be obtained by using this circuitry. Now this 3-phase AC supply, 50 Hz AC supply, can be converted into DC by using the converter. Then this DC supply can be inverted with a 3-phase variable voltage, variable frequency, and that is fed to the 3-phase induction motor. In this way, the wide range of speed variation can be obtained with a moderate efficiency and power factor. So in this way, we have finished this method. Now see the rheostat control. Now this method is generally used for the slip ring induction motor. Now pay attention. Now for a 3-phase slip ring induction motor, stator is always stator may be either star connected or delta connected, but rotor is always star connected in order to add the external resistance in the rotor circuit via the slip rings and process. For simplicity, I have not shown here the star connected rotor winding. Okay, these are the slip rings and brush arrangement, and this is the speed controller starter or a rheostat, a star connected rheostat. Okay. Here at this position, the maximum resistance is in the circuit. If we add the external resistance in the rotor circuit, the speed decreases. And what happens to the torque? Already the torque is proportional to K S upon R. Already we have learned this one. So for a constant load torque, S1 upon R1 equal to S2 upon R2. Where therefore S2 equal to R2 into S1 upon R1. Here R2 is greater than R1 because this here it is a resistance of the rotor after adding the external resistance. And therefore what happens here? The slip increases. Therefore slip increases, speed decreases. So in this way, by adding the external resistance in the rotor circuit, the torque increases. But no doubt here the speed falls. Now this method is generally or less it is used because of the disadvantages, that is the rotor resistance R2 increases, the copper losses I2 square R2 also increases, thereby efficiency decreases, and therefore the speed depends on both the factors, rotor resistance as well as load, and therefore it is used only where the speed changes is needed only for a short period so that losses will be limited. Now the next method of the speed control of the three-phase induction motor, especially for the slip ring induction motor, is cascade operation. The principle of operation, here the two motors are used. Two motors, pay attention, two motors are used and which are mounted on the same shaft. Two motors, motor A and motor B are mounted on the same shaft, and for the motor A, the turns ratio, stator turn to rotor turns ratio is 1:1. Now when the motor is fed by the three-phase supply from the grid, now whatever the EMF generated in the slip ring, that will be nearly equal to the supply voltage. That is the back EMF generated. And the same is fed to the motor B. Same is fed to the motor B. Okay. Now here such a combination can be operated as a 4 combinations separately. First combination is, there are 4 combinations are possible. The 4 possible combinations are, let us, motor A is working independently. So NS is 120 F upon P, it is a usual. So NA equal to 120 F upon P. Now motor B can be used independently with only feeding the supply from the grid. So these are the 2 possible combinations. The third combination is by connecting them in a cascade, cumulative cascade connections, the speed AB, NAB equal to 120 F divided by P1 plus P2. And the last one is differentially cascade, that is NAB equal to 120 F upon P1 minus P2. Okay. So what happens here? The motor A, when the supply is fed to the motor stator winding of the motor A, it will generate the EMF across the slip rings. At the beginning, at the time of starting, the frequency of this EMF induced at the slip rings is same as that of the supply frequency, and which is fed to the stator winding of the motor B. So the motor, and they are on the same shaft. Now as the shaft catches the speed, what will happen? The frequency of slip ring EMF induced at the slip ring decreases, and thereby it controls the speed of the motor B. So in this way the speed control is possible. We will stop here. Thank you very much.